session. Welcome to the session. We are going to do session 6 today. I hope I've chosen the right session. And it's going to be on geometry. So some of these problems are quite challenging, and I hope you learn a few things. All right, so let's go straight to the to my screen. And I'm going to share my screen with you. Okay, can you see this screen, Koso? Can we?
Yes, I can see the screen, Prof.
All right, then I presume that everybody can see the screen. Okay, let's go to the very first problem. The first problem is the following. There is a sketch given with a shaded area, and the question reads, in the sketch, the star, the vertices of the star lie on the vertices of the square or on the midpoints of its sides. Well, I think we can see quite clearly this picture. So the vertices are either at the all right. So you got a star here, and this is a shaded region. What fraction of the square is shaded? So you've got the yellow part, and you got the whole square, and you want to know what the fraction is if you take the yellow part over the entire square. Now you will see the shaded square looks like a rather clumsy figure. You know, it's not anything that is recognizable, a circle or a rectangle or anything like that. So we have to think about this problem and see how best we can tackle it. Now, no numbers are given, which is quite unusual because we're not given anything here. But the clue is that we are talking about a fraction. So when you got a fraction, it means you're taking the ratio of two sides or two numbers. And usually when you take the ratio of two numbers, then it doesn't really matter what the original sides are. But what I'm going to do is I'm going to assume that, you see, I know that these sides are equal. All these are equal. Because this is the midpoint. We've got the midpoints of each sides. So we got that these sides are equal. And you will see that yeah, so the area of the yellow part is what we are looking for. All right. Now, we know that these two are equal. If you want to give names to this, you can call this A and A. But I prefer using numbers, so we can call it 1 and 1. But it turns out that if I use 1 and 1, I'm going to get fractions. All right. Maybe it's not a problem. So let's call this side A here. This is A. So this is also A. All right. Now, we can see the area of the square. Once we give the names of these sides. So the side of the square is 2A. So its area is 2A all squared, which is 4A squared. All right, so that's the area of the square. Now we need to know what the fraction of the square is shaded. So we need to know what is, the question here is, what is the yellow part over 4A squared? That's the area of the yellow part over the area of the square. So we need to find what the yellow part is. Okay, and the yellow part plus the white part The yellow part plus the white part gives you the whole area. Okay, so what I need to do is to get the yellow part, I need to work out the white part. Now the white part consists of, now that's very much easier because you've got, the white part consists of several triangles. In fact, there are 8 triangles, 2 there, 2 there, 2 there, 2 there. So you've got 8 triangles. And they all sort of look like right angle triangles, which makes it very nice. It means that we can find the area of these triangles if you know the base and the height. So let's call this x and let's call that y. So the area of this one triangle is half xy. But now I want you to notice that all these triangles are actually congruent. They all got exactly the same lengths and same angles. But that's not very easy to see straight away. We have to look at some angles here. Like for instance, let's call this angle here, say, dot. Let's call this dot. Okay. Now, if you look at dot, it's in this triangle, and suppose we call this curl. All right. Now, you'll notice that this triangle here, this large triangle here, its sides are A, 2A, and it's a right angle triangle. This one here has also got the same kind of a thing here. Right? It's A, 2A, and a right angle. So this triangle that I'm pointing to, I hope you can see it, is congruent to that triangle because you got 2 sides and an included angle, which means that okay, even before that, uh, you can see that this triangle here, this one, let me suppose I take this triangle here. That triangle has got sides A and 2A also. And that triangle is also congruent to this triangle here. Because these 2 triangles have also got sides A, 2A, and a right angle. Right, which means that this angle here, this small angle of this large triangle, is equal to the small angle of that triangle there. So this part here is dot. See? Because it's the angle between the hypotenuse and 2A, and here this angle here is also the angle between the hypotenuse and 2A. And also, as I told you before, these two, this is also dot for the same reason, because this triangle here is congruent to this triangle here. So this is also dot. So you got various dots here. And this curl, now notice that dot plus curl is 90 degrees. See, dot plus curl are 2 angles in this large triangle. That's 90 degrees, because the remaining angle is 90. Which means that in this small triangle, dot plus curl is 90. Now that's very nice, because it means that this small triangle is a right angle triangle. See, because dot plus curl, I'm calling these, I'm not giving them names, call this curl, is the same as dot plus curl there. And these two dots are equal because of congruency. So this angle here is 90 degrees. Okay? But more than that, the small triangle here, its angles are dot, curl, and 90 degrees. And in the large triangle, this one here, the red triangle which I've drawn, its angles are also dot, curl, and 90 degrees. So if you know similar triangles, we have spoken about similar triangles before. These two triangles have got the same angles, which means that the sides are in proportion. Now, the large triangle, you will notice that the long side is twice the short side, because this is 2A and this is A. For construction, this is the midpoint. So long side is twice the short side. So even in the small triangle, which is similar, the long side Y will be twice the short side. Somebody is writing on my screen. Can you please stop doing that? If we identify you, then we are going to ask you to leave the classroom. Please don't do that. And please rub it out if you have been, if it's yours. Now you messed up my screen. Please erase your yellow lines. Okay, so what we've got here is that this line here, Y, is actually equal to twice X. See? Y is equal to twice X. Now, like that, now you can see all these triangles. The same argument can be used for all these triangles. The sides will be X, Y, and dot, so they're all congruent, all these white triangles. Right. So therefore, the W, the white part, is 8 of the white triangles. The white triangles. And now we know what the area of the white triangle is. Each white triangle is a right angle triangle whose sides are X and Y. So the formula is half base times height. So it's half XY. Right? But we said Y is 2X. So if Y is 2X, then the 2's cancel. Or if you want, you want to put 8 times half is a 4. And XY is X times 2X, which is 2X squared. So, so this is actually 8X squared. So the white part is 8X squared. But now, look, this is a right angle triangle. So we know that X squared plus Y squared is A squared. Right? And Y is 2X. So this means if Y is 2X, I don't have space. The Y is 2X. 2X all squared is 4X squared. So you got 4X squared plus X squared is 5X squared. So I'm going to go into this corner here. Sorry about this. So I got 5X squared is A squared. And therefore X squared is A squared over 5. All right, so that tells me that the white part is Y plus white part is 8X squared, which is 8A squared over 5. I'll put everything in terms of A. Now that person who has written these white lines here hasn't taken it off yet. Kotso, I don't know whether you can identify that person. If you do, please take him out, and I don't want him to be in this class again. We'll take him completely out of this list. He hasn't taken out these yellow lines. He's messed up my screen. So Y is, this white part is 8A squared over 5, and therefore you can work out what Y is, and then Y 4 minus something. All right. So you can work, you see that Y is 4A squared minus 8A squared over 5. And that is 20a squared, 12a squared over 5. So now that you got the y, the actual one, what you're looking at here is, yeah, so you can substitute here, and you will see that you got your question mark is the area. Sorry, I allowed myself very little space. The question mark is y over 4a squared. So you can see y over 4a squared is 3 over 5. Because 4a squared times 3, you've got here, and y over 4a squared is 3 over 5. So this is the answer. The area of this is 3/5. I don't know whether my calculations were right. I hope it's correct. But you got an idea as to how to solve this problem, right? It's not an easy problem. You have to first identify what the problem is, and then you say, I need to find the white area. And that you have to do a little bit of geometry to eventually get to that. All right, so to get to my next picture, oh no, my next problem, these problems are quite advanced, so it'll take me some time to solve each of these problems. The geometry problems that I've chosen are advanced geometry problems because we are dealing with you going into the third round. So these are not trivial. So here you've got a circle, and you got another circle inside it, and it's given that O is the center of the circle. This one is the center of the large circle, and you got this other circle which is sort of touching it exactly, and you want to calculate the area outside the smaller circle. In other words, you want to work out the area of this moon-shaped area, right? So the only things that are given is that this part here, the small piece here is 18, and that small piece is 10, right? 18 is just this little stretch, this little strip here, and this is 10. Those are the only things given. Interesting. So how do you find the area of this moon-shaped area? How do you find that? All right. Anyway, one thing we know is that moon-shaped area is let's call it A. So that area that we're looking for, if you add it to the area of the small circle, right? You're going to get the area. I'm sorry, if you add it, you're going to get the area of the large circle. Right? The area of the small circle plus the one that we're looking for is the area of the large circle. So how do you find the area of a circle? Well, you have to, it's pi r squared, where r is the radius. So we need to give a name to the radius of the small circle. So we'll call it small r for radius. It's the radius of small circle. And for the radius of the large circle, we'll call it capital R. Okay? Capital R is the radius of the large circle. All right, so in other words, what we need to do is to calculate the A, which is the area of the large circle, which is pi r squared minus, that's the area of the large circle, minus pi small r squared. So that is what you need to do. So we need to calculate these two radii with the given information. All right, so that seems to be quite a problem here, but let's see what do we have. We want to use this small piece here, 18. Let's look at that 18. I can see that when I take 18 and I add it to the diameter of the small circle, oh yes, The small circle has got center along this line here. You can see. So if I add 18 to the diameter of the small circle, I'm going to get the diameter of the large circle. I think that should be quite clear. 18 plus this thing here. The diameter of small circle is twice the radius, and that is equal to this entire thing, which is twice the big radius. So now we've got a nice, neat little equation with small r and capital R. And when you divide by 2, you get 9 plus small r is equal to capital R. So you have that. When you take it to the other side, you get the capital R minus small r is 9. So that's useful. Or otherwise, we have now, and this is very nice. Whenever you have a thing like this, then we got the capital R in terms of small r. And that means now I can eliminate capital R from my calculations. I only need to calculate small r. And if I can calculate small r, I would have calculated capital R, and then I would be able to find the area. Okay, so now we still need an equation involving small r. And how do you do that? Now, the trick is you have to join, you see, I want to use this 10 here. Now, how do I use the 10? I can use the 10. When I go right down here, then this is vertical. It's given that this is 90 degrees. So I've got a right angle here somewhere. It's a right angle. So it seems as if I'm going to land up with Pythagoras somewhere to get the equation that I'm looking for. All right. So what I do is, to get Pythagoras, I need to draw a right angle triangle. So I want to use this 10 here. So why don't I join those two? Then I will get a little right angle triangle and see whether I can use the information to get an equation involving this. Okay, so we've got a nice little right angle triangle here. Right. So do I know the sides of this right angle triangle to get my Pythagoras? Well, certainly this part here is known because it's the radius of the small circle. From here to here, it's the radius. Okay, so do I know anything else? Well, let's have a look at this part here. Well, I can see that, oh yeah, okay, this is not bad because this one here is equal to this entire line. This is a capital R. See? This is capital R, and from here to here is small r. So, which means, because this is the radius of the small circle, and O is the center of the large circle. So this side here is capital R minus small r. And I'm going to rub that off so that I take that out. Right. So this is capital R minus small r. But capital R minus small r is 9. Okay, now that's beautiful. So this part here is 9, right? Now, as far as this is concerned, this is always the center of the circle. So this whole thing here is the radius of the large circle. So this part here, the other side of this triangle is r minus 10, this whole radius minus the small piece. So let's have a look at that. I'm going to wipe this thing out. I need space. So the vertical red line is the radius of the large circle minus this piece there. So this is r minus 10. All right. right, so we've got the sides of this right angle triangle. So we have, oh, but capital R is, we know it's in terms of small r. I told you earlier on, capital R is not there anymore because you can write it in terms of small r. So this is, capital R is R plus 9 minus 10. So it's R minus 1. 9 minus 10 is negative 1. So there you have it. You have in this right angle triangle, you got one side is 9 and the other one is R minus 1. And you got R. So you got an equation involving R. So it's 9 squared, right? That's Pythagoras plus R minus 1 squared is equal to small r squared. Okay. Okay, and that tells you got 9 squared is 81. You got an r squared minus 2r plus 1 here, and you got an r squared on this side. The r squareds can cancel. That minus 2r plus 1 on this side comes to this side, so it becomes 2r minus 1. I did that quickly, but it's easy to come to that. Now there it is. You don't have a square term here because the square terms disappear, and you've got 81 equals this. Bring 81 to the other side, you've got 82. 2r is equal to 82, and small r is 41. Small r is 41. And there you have it. You got small r, and if you got small r, as I told you earlier on, then capital R is also known because it's, you can write it in terms of small r. So it's 41 plus 9, which is 50. So therefore, your A, which we're looking for, you got a capital R and your small r. It's pi into your capital R squared, which is 50 squared, right? This minus 41 squared. All right, because small r is 41. So now this is the difference of two squares. You don't have to work out this entire thing. This is pi 50 minus 41 times 50 plus 41. Right, difference of two squares. 50 minus 41 is 9 times 50 plus 41 is 91. So you have this 819 pi. 9 times 91 is 819. So that's the answer to this question. All right, so it's quite an interesting question. We had to think a bit to get to an equation. The whole idea, a lot of things in mathematics boil down to equations. Try to get an equation and solve. That's why you study solutions of equations, quadratics and linear equations and all kinds of equations, simply because most of the problems reduce to equations, and that high school tells you how to solve them. Okay, so we used all the information quite nicely to get to the answer to this problem. So let's get to the next one. Okay, now here, you are given ABCD is a quadrilateral, ABCD. Angle C is 90. This angle here is 45 degrees. This angle is 125. Now that's not very nice. 125, we don't know much about it. And this is 55. One thing you can see is 125 plus 55. When you add, we get 180, which is really nice. So maybe somewhere along the line we should be using that. There is a way of using that information to actually solve this problem, but I prefer not to do it like that. Okay, now you've got BC is 20. It's given that this is BC is 20. Okay. I have to admit that I took some time to solve this problem because there are different ways of doing it. But there is definitely constructions involved. You can't solve this problem as it is. you are asked to find the area of this quadrilateral, ABCD. Okay, so the area of the quadrilateral, this quadrilateral consists of two pieces. And so you can say it's the area of this triangle plus this area of this triangle. But this area of this triangle is very dicey because you don't know. You got 45, 125, and some other angle. How do you find the area of this rather, funny looking triangle? So as it stands, it is, you cannot solve this problem. You have to perform some constructions. And I found that the best construction to do is the following. You see, you got a right angle triangle here, and what I do is I create a right angle triangle, a larger right angle triangle, by extending this thing to get a new line which is 20 units long. In other words, I want to create an isosceles triangle at this spot. And to do that, I have to, I'm going to extend CD to make that new line 20. It's not quite clear at this stage as to why we do that. But as I said, these geometry problems, it's only after a lot of trial and error that you come across a solution which is nice and neat. There are other solutions. Now, even here now, it will take some time before we can get to that. But what I do know is I've extended this so that this is 20. Right. Now, the area that I'm looking for is this area here. And what I'm going to do is join, I want to create this isosceles right angle triangle. I've got 20, 20. So I'll force a triangle, I'll join that. And I know that this new triangle that I have drawn, this is a construction, is extend CD to a new point, which we can call E. All right. So that CE is 20. So that's a construction. When you're writing it out, that is how you'll say it. But now you have a right angle triangle, which is isosceles. So the other two angles add up to 90. So each one is 45. Now, this is where this whole thing suddenly becomes, the reason why I did this becomes quite clear. Right. Now, if you have done circle geometry, and you're all senior students, you will see that you got these 4 points, which I am indicating. Those 4 points, you can see 45 degrees here and 45 degrees here, which means that this side or this line segment subtends equal angles at A and E. And when you do circle geometry, whenever you have any one side of a quadrilateral subtending equal angles at the other 2 points, then you have a cyclic quadrilateral. You have a cyclic quadrilateral. So this quadrilateral BAED is cyclic because one of the sides subtends equal angles at the remaining 2 points. Okay, now this line which I've drawn here, it actually turns out to be parallel to BD. This new line is parallel to BD. And how do you see that? See, I'm going to calculate now, because this is a cyclic quadrilateral, this angle here becomes an exterior angle of the cyclic quadrilateral. You see, this is BAED, and if you extend it, you get 55. 55 is given. You were given 55 and a wuzwa. So, it's already 5:40 and this person is about to come into this class. The rule is if you come after 20 past 5, he's not allowed. But just allow this guy and let him be the last one also. Okay, so but this is an exterior angle of a cyclic quadrilateral. So it'll be equal to the interior opposite, and the interior opposite angle is that one. So this whole angle here is 55. This angle here is 45. So this angle must be 10. Because this whole angle is 55. Right? It's equal to this exterior angle of the cyclic quad. Okay, so you got that is 10. Now, it is also given that this angle here is 45 here, from here to here. So I'm sorry, 125. This angle from here to here. So this whole angle here is you got 45 degrees. You got 125 degrees, which is 170. If you add these two. So this angle here, the remaining angle, will have to be 10, because the sum of these two angles is 170. And therefore, the remaining angle will be 10. And there you have it. You got that angle is 10, and this angle is 10. But these two angles are alternate angles. See? It's quite a deep problem. We're using a lot of interesting theorems, cyclic quadrilaterals, in particular. And you see these two lines are parallel because they are alternate angles. All right? Okay, now, when you've got two parallel lines, now these two parallel lines, BD is a line segment on one of the parallel lines, and we are looking for this white triangle. If you remember, the whole purpose of this is to find the area of this triangle here. Before I had all these other lines coming in, I needed to find the area of this funny looking triangle. And I said, look, you can't find the area of this triangle because it's a strange looking triangle. But now this triangle here in this figure now has got this base and it's between these two parallel lines. So the area of this triangle, which you're looking for, is the base times the height. And therefore, its area will be equal to this triangle here this point is also on that parallel line. So these two, that yellow triangle is equal in area to this red triangle because they have the same base and they're between the same parallel lines. Okay, so what does all this mean? It means that if I call this part here A, the required area of ABCD is A plus the yellow triangle. Because we said originally it's that, right, plus the yellow triangle. So this is the same as A plus red triangle. Because we said that this red triangle has got base that, and it lies between the other 2 points on the parallel line, so they got the same height. But now A plus red is now the area. When you add A to this red triangle, you get the area of triangle ACE. Right? A plus the red triangle, I'm sorry, it's ABE. ABE. Right? A plus this triangle AB, not AB, it's CBE, sorry. CBE. All right. But we know this CBE by construction, the area of that is a right angle triangle, right? Isosceles triangle is half 20 times 20. Right? Because this is the area of the triangle which we created right in the beginning. and that's 200. So it's quite a long-winded process to get to the area of this triangle. But if you perform this construction, you will get to the answer. Now you will say, oh my God, how can we do all these things? Unfortunately, geometry is like that. And at the advanced level, you are expected to do a lot of problems in geometry and try to find which constructions work. This is not the only construction which works. There are other constructions, right? You can try it out and see whether you can find some other constructions using the information that is given. But one of the things will be nice will be to extend this line AB, because you got 125 here. And when you extend it, the remaining angle will be the same as 55. So you might get a nice isosceles triangle there somewhere. All right, so let's go on to the next problem. Okay, we are now in question 4, and we've finished half the time. These are quite deep problems. Now, if you look at this one, you've got a square like this, and you got another little square drawn here, and this corner piece is called S. Right? It's a little square there. Okay. Now another square is drawn like this. It's like a vertical square, and the diagonals. This diagonal is parallel to this diagonal, and this diagonal here is parallel to that diagonal. So you got a sort of square which is tilted by 45 degrees. Essentially, that's what you've got. Okay. Now the question is now to find the area of the square, given that the area of this original square is, its side is 27. The area of the original square is 27. Its side is 27. So S is 27 squared. So you know the area of this. Knowing that, how do you find the area of this tilted square? Now, instead of looking at this thing here in this large, in this thing, I am trying, what I do is I isolate this and that and put it into another bigger picture, where what I do is actually complete the square here. I try to complete the square here, like that, like that. So you've got a bigger square here, and so it's like this square T is sitting inside this larger square. All right. You can see that this T, I've got it here. All right. Actually, I don't need all this complicated. I think I can do it in a much easier way. If I do this, okay, so I've got the midpoint here, midpoint here. So what happens here is you got a this is my T here. You can see all these are equal. So the T is actually equal to, see, these are those, I can see that I'm going to get 8 of these triangles here. Right? 8 of these exactly the same triangles. So this part here, this white part, it consists of four, four quarter squares, right? The T consists of 4 Okay, for the third time, I'm going to say this. Mm, I'm losing track of my own arguments here because it's being. Okay, so the T is a half of this entire square, and the area of the square is 2x, the size is 2x, so it's 4x squared. So it's 2x squared. The area of T is 2x squared. Now, we know that S is this part here. You see this S, it's this part, this square here. All right. So now, what is the area of the shaded part? Now, if you look at this part here, the diagonal of this square here, the small square, if you draw all these, draw them nicely, this dot, 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 you will see that this diagonal of this S square, diagonal of S, is 3/4 the diagonal of T. And because there are 3 pieces which make up the diagonal of S, and the diagonal of T is 4 of those pieces. So the diagonal of S is 3/4. But there is a connection between a diagonal of a square and its area. You see, if you call this A, and if you call this A, so the area, the, the area of the square is A squared, and the diagonal squared, let's call it D squared, is 2A squared. So the square of the diagonal is twice the square of the side. So this here, the square of the diagonal, if I'm squaring this, right, the square of the diagonal is twice the square of the side. And we saw the side was given, the side of this, of S was given as 27. They say here, the length of the side of the square is 27. So it's 2 times 27 squared is equal to, when you square the 3/4, you get 9/16. And the square of the diagonal of T is the square, is twice the side, twice the twice the square of its side. But the side of t is 2x. I'm sorry. The side of t is that one there. Okay, so it's twice. Sorry, it's twice this squared. Let's call this b. So it's 2b squared. But b squared is x squared plus x squared. So it's 9/16. And b squared is 2x squared. So it's 4x squared. Because this side of this t is t squared is that squared plus that squared by Pythagoras. So it's x squared plus x squared. So it's twice that. So you get 9/16 of this. So it becomes 9x squared over 4. Okay, so that can, from there you'll be able to work out that what t is, because the area of t is twice x squared. So x squared, it's 2 times 27 squared, right? Divide times 4 divided by 9. We make x squared the subject, but we want to work out the area of t is twice this. So you have to put a 2 there. Okay, and then when you work this whole thing out, you'll get 648. Okay, it's a maybe you don't need the 2 there. Okay, so it's a quite a complicated problem, but it's dividing a square up into several small pieces and trying it. Okay. All right, so these, as I told you, these are quite demanding questions, and I put them right at the front. And that's taking a lot of time. Now, let me now get on to the next question. We go on to question 5. In the sketch, A, B, G, H, I. So you got this outside one is a regular pentagon. And it's a regular pentagon. It's a 5-sided figure. And A, B, C, D, E, F is a regular hexagon. So this is a 6-sided figure, as you can see. And the question is, what is the size of IAF in degrees? Now, I think this is, fortunately, this is not so difficult. The important formula here is that the sum of the interior angles of a polygon, any polygon, having n sides is 2 n minus 4 straight angles. By straight angles, I mean 180 degrees. It's easy way. It's an easy way of expressing it, right? So 2n minus 4 straight angles. Like for instance, if n is a polygon having 3 sides, that means it's a triangle, and the sum of the angles of a triangle, according to this formula, n equals 3. 3 times 2 is 6. 6 minus 4 is 2. And 2 straight angles is 2 times 180 degrees, which is, oh, wait a minute. So that's 360s. So it's actually n minus two straight angles. Yeah, let me do. I got the wrong formula here. It's n minus 2 straight angles. Sorry about that. So there's a nice simple formula. If you know the number of sides, then you subtract 2 and multiply by 180 degrees. So for a quadrilateral, 4 minus 2 is 2. 2 times 8, 180 is 360. And we know that the sum of angles of quadrilateral. So here you got the hexagon. Now these are regular. Regular means all the angles are equal, right? So the sum of the angles of a regular, so you have each angle of a regular polygon all the angles are equal, and the sum of all those angles is n minus 2. So it's n minus 2 divided by n, right? Because you got n sides in a polygon, and therefore there are n angles. And when you add up those n angles, you're going to get n minus 2. So each one is n minus 2 over n. So therefore your hexagon, like let's look at this angle that we're looking for is this whole angle, the angle of a pentagon. Let's see, pentagon. N is 5. 5 minus 2 is 3. 3 over 5. Straight angles. And that's 180. So when you take out 5 goes in 180 36 times. That's 180 degrees. So therefore, FAB, angle FAB, this outside angle is 108 degrees. And the hexagon angle is the smaller angle. Right? Now you got the hexagon is the outside side. Okay. The hexagon has got 6 sides. So you have 6 minus 2, n is equal to 6, divided by 6 now. That's 4/6 of 180. That's 120 degrees. Yeah, so this is actually IAB, right? Because it's the angle of the pentagon, and that's IAB. And now this is FAB, right? And that is 120. So the angle that you're looking for, that small one, so the answer is just the difference between these two, because it's the answer is 120 degrees minus 180 degrees. Right, so the large angle is 120, the smaller angle is 108, angles of a regular polygon. That's a straightforward formulae, so there's no problem. You should have no problems regarding that. So let's get on to the next problem, which is question number 6. Right? What is the height of a stop sign, which is a regular octagon with side 50 centimeters? Okay, I've drawn the octagon. Khalsa, please don't admit this person. He's coming at 6 minutes past 6, and he's not going to gain anything. Please don't admit him. And that goes for everybody else who comes late. We said the cutoff point was 20 past, I think, or even 10 past, I'm not sure. But they come that late and disturbing us. We should not allow people like that. It's a waste of time coming into the class at this late hour. So you've got an octagon, which has 8 sides. You can see this outside figure has got 8 sides. And the sides are all 50. The interesting problem. If all the sides are 50, stop signs have got a shape of an octagon. octagon, octagon, or whatever. So all the sides are 50. So the question is, what is the height? In other words, if I draw the full length, the height will be this one here. So you are talking about this entire length here, right? To be the height. Okay, now we can see if I complete this on this side here, you'll see that what we have here is the same picture here as you have there. So this is also x here, right? This is x. And this is 50, so this will be 50. Because this is a rectangle here. So therefore, the height that we're looking for is equal to this entire thing is 50 plus x plus 2x. Okay. So the problem is to find x, where x is, when you join these two diagonals, you will see where you get a right angle triangle. Why is this a right angle triangle? Because, well, you can try to prove it. It's not very easy to prove, but in an octagon, the interior angle is 135 here. See, and one can show that this is 45. So therefore, this is isosceles because this is 90. You see, yeah, you can prove all this, knowing that all the sides are and the angles are the same. That helps you to prove that this triangle here is the right angle triangle. I'm not going to go into that, but it's a good exercise for you. You can check it out by using congruence. All right, so therefore we've got a right angle triangle here, and the sides are x, so x squared plus x squared using Pythagoras is 50 squared. So now you can calculate what x is, because you have Pythagoras gives you formula 2x squared is 50 squared, which is so x squared is 50 squared over 2, and therefore x is 50 over square root of 2. 2x squared is this, so it's 50. So the square of that, so this x will be 50 over the square root of 2, and therefore your height is equal to 50 plus x is 2 times 50, 100 over square root of 2. So that is your height. It can be simplified a little bit further, but that answer will also be accepted. 50 plus 100 over square root of 2. Okay, so that's not such a difficult problem, but you just have to know the properties of octagon. So just remember that when you join all these things, you're going to get a very nice picture. All right? When you join all this, you have a little square here, you'll have 4 rectangles, and you got 4 isosceles right angle triangle here, and the whole lot. You see, one of the ways of seeing why this is x here, which I had a nice way of doing it and I forgot it, but now I remembered suddenly. You see, when you have this regular octagon, you can actually extend that, and this is 135. So when you extend it, this angle here, this will be 45. And when you extend this is also 135, the interior angle. This is also 45. So these two exterior angles are both 45. So therefore, this becomes an isosceles triangle. And this is 90 degrees because it could 45, 45. So you got a square here, you see? This whole thing becomes a square. So that is why you have these two sides are sides of a square and they are equal. That's another way of looking at it. But it's nice to know all these properties that the octagon can be created by cutting off the corners of a square. All right, cutting off the corners, and you can get a regular octagon. It's got some nice geometry around it. Okay, so let's now get on to the next problem, which is this one. It says here that the volume of a cube whose diagonal is given by some funny looking number here, the cube root of 17 times the square root of 3, and the question is to find the volume of this cube. Let me just draw a much larger picture. Maybe I made it too large. Sorry. Right, I'm going to redraw this cube. Maybe I can use the same picture. All right. Now you've got a cube, right? So all the sides are the same. You got x. And you got a diagonal. You're joining one corner of a cube to the other corner. Now this kind of question appears quite frequently. But what you have to understand here is the following. When you're joining these 2 points, this line here is going inside the space of this cube. It's not sitting on any side, right? But you can, now what is important is that this part here is a floor. I've spoken about this before. This one here is a floor, and you can join, if you join this point, this is also on the floor. So both these points lie on the floor. So when you join this, you're going to get a line on the floor. And now you got a line on the vertical wall. So this PQ becomes the diagonal of a right angle. Yeah, it's because you got a floor and you got vertical, this line here is perpendicular to every line on the floor. I certainly told some class about this, and I suspect it's this one, so I won't do this thing again. So this line here, this angle here is 90 degrees between POQ. Right? It's a triangle, and POQ is 90 degrees. And therefore, you got a right angle triangle here, and this bottom one is the diagonal of a square, which is the square of the base. You got XX, the diagonal of a square. So this PQ squared by Pythagoras is x squared plus OQ squared. Right? Because this triangle is a right angle triangle. So PQ squared is x squared plus OQ squared. But if you look at OQ squared, OQ is a diagonal, is a hypotenuse of another right angle triangle on the floor, because this is a square at the bottom. So OQ squared is x squared plus x squared. Because it's a diagonal of the square on the floor. So in the end, you get 3x squared. Right. Now, we know the reason why I call this thing x here is that I know the volume. The volume that you're looking for is the volume of a cube. If I'm calling this x, it's the side of a cubed, right? Length times breadth times height is x times x times x, and that's the volume of the cube. So we are looking for x cubed. So we've got PQ squared is this, but PQ is given. Now you've got 3x squared equals PQ squared. And I'm looking for a cube here. So why don't I okay, if I want, I can work out x first. So x squared is PQ over square root of 3 because x squared is PQ squared. So x squared is PQ squared divided by 3, so x is the square root of that. We already have PQ. PQ is the cube root of 17. Times square root of 3. Divided by square root of 3. That's very nice. That cancels off. So you have x is equal to the cube root of 17. But I want x cubed. So that's easy now. If x is cube root of 17, so x cubed is 17. And that's what I was looking for. The volume of this cube, which is the side cubed. Okay. So that takes care of question 7. And there you found the diagonal of a cube. So just remember, even if you don't have a cube, if you have a rectangular, what's called a prism or something like that, the diagonal can be calculated exactly the same way. You have to join one of the diagonals of the base and get a right angle triangle, and then use Pythagoras to calculate the diagonal, like the way we did here. Okay, so the next problem is so they say here the adjacent sides of the shape below are right angles to each other. So you got this shape here, a kind of you can cut out a cardboard shape like this, and then this part here is cut out. The triangle is cut out, and this triangle is cut out. And it's turned around like this and placed here. Right. So if this triangle is cut out and stuck here in the corner. Along this line here, you see? It's stuck here. So what it means is that this part here is 11. So this part here is x. And this is 11 here. I see. The 11 is still here. So there it is. This is cut out and put there, right? There it is. It fits in exactly into this. And then this bottom part here is put in here. So you've got, I'll just put this, make these in different colors so we can see what's going on. This cutout piece is stuck here. It's the same as this. Right? In this larger picture here. Okay. And then this here is x and 11. So all right. So the problem is to find the value of x, right? Which we don't know. This x here is now inside here. X is equal to DF, because this triangle has been pushed into that. Okay, and so there's 11 here, and this is X. So you got 11X and 90 degrees. So this whole thing here is X. Now, so what is X? Now you see, this is 11, this is 13, so this is 24. From here to here is the same as the sum of these two. Now this part here is now goes in here. So this part here is 24, you see. Because these two triangles are congruent. These two red triangles, because it's the same thing has been cut out and put there. So obviously it's the same triangle. So it's they're congruent. So if this is 24, that is 24. Okay. So X is actually, this is 13 here. So X is 13 plus 24. And this is a problem which requires imagination. Okay, the X is now translated to this dotted line here, right? And the dotted line is up here, right? And this dotted line consists of two pieces. One is this and the other is that. We already know the one piece of the dotted line is 13. The only thing is you need to work out what the other one is, and there's no need to work out anything because these two triangles are congruent. It's the same triangle, so that's 24. Okay, so that requires a little bit of imagination to solve that problem. All right, so let's get on. The next problem is the following. KAST is a quadrilateral with KA equal to KS. KA equals KS. Okay, so I've drawn KA equal to KS. Angle AKT is 80 degrees. AKT. Okay, immediately I can see this whole angle is 80 degrees, right? AKT. But this is an isosceles triangle. So if this is 80, these two angles add up to 100. So there must be 50 each. I'm going to write down the information as I get it along. All right, so you got, this is 80, and each one is 50. Now, it's also given that KAS is 75 degrees. KAS. So this is 75 degrees. Oh, wait a minute. Sorry, we were not given this. I beg your pardon, just hold on, please. Hold on. It's only given that KA equals KS and AKT is 80 degrees. KAS is 75. So sorry about this. So these two are equal. So therefore, this triangle here is isosceles. And we got one of the angles, KAS is 75. So therefore, this angle here is 75. Just ignore this one here for the moment, please. We're only given that these two are equal. I can't seem to be knocking this thing out from here. Okay. So that angle there is 75, and the whole angle there is 75 also. This angle here is also 75. Now it's given that this angle here is 65. This angle is 65. And this is 75. So if this is 75 and this is 75, so these two angles together add up to 150. So we can calculate this angle here, 30 degrees. Right? Because both of them 75. But we are already given that angle, given also that angle AKT is 80 degrees. So the angle AKT is 80 degrees. So if this is 30, this now becomes 50. Right? So this angle is 50 because the whole angle is 80. It's also given that angle KTS is 65. So KTS is 65. This whole angle here is 65. Okay, so you got this is 50, this is 65, and the three angles of a triangle add up to 180. So therefore, 50 plus 65 is 115, and the remaining angle will have to be 65. Also, because this is 50, this is 65, this has to be 65. But now these two angles are the same, and therefore we can conclude these two are the same. You see, originally I told you ignore the fact that this equal to this. We can actually prove that these two are equal. You're only given those two, and we eventually can prove that these two are equal. And the problem was to find angle ATS, which is ATS. So this one here, this angle 1. You're supposed to find out what that angle is. So now that you know that this angle is 80 and these two are equal, you just prove them. So these two add up to 100 degrees. And therefore, let's just do that. This is 80. These two angles add up, they're equal, and they add up to 100. So each one must be 50. The whole angle is 65. So this one here is 15. Okay, so it's a lot of what you call angle chasing. You got isosceles triangles, but be careful, don't make the mistake that I did to make any assumptions. You use only the given information. You got isosceles triangles, therefore the base angles are equal. And if the base angles are equal, the sides are equal. That is what we used. So that problem can be done. It's what we call an angle chasing problem. No constructions involved. So it's a kind of question that can appear in a school paper because there are no constructions involved. Now the next one. Okay, we already had our first 6. Let me just quickly do this. Given any 4 points on a plane such that no 3 are on the same straight line, in other words, they all form triangles, what is the maximum number of acute angle triangles possible with the vertices among these given points? So here you got constructions which how many acute angle triangles can you draw in this setup? You got 4 points, no 3 which lie in the same straight line. Now I've actually constructed 3 acute angles here, acute angle triangles. The triangle will have to be, the vertices will have to be the vertices of this. So if you look at this one here, I constructed them in such a way that they all add up to 360, by the way. Actually, I just drew a kite here, and it worked out quite nicely. So you have, this is an equilateral, I'm sorry, a triangle with acute angle. There's another acute angle triangle here. And then this last one at the bottom is also acute angle because this is 84, 48, and 48. By acute angle triangle, you mean all the angles are acute. So you can draw a triangle, the 4 points, where there are 3 acute angle triangles. But you know, there can be only 4 triangles altogether. you see, if you got 4 points and you're going to use the vertices, then you can get only 4 triangles. How do I know it's 4 triangles? All you have to do is to remove one vertex, and the remaining 3 will form a triangle, right? And you remove that vertex, you'll get a triangle. You remove that one, you'll get a triangle. Remove that one. So there are 4 triangles altogether that can be formed with the vertices. You can draw 3 acute angle triangles, but now the question is, they say, what is the maximum number? So the question is, can you draw 4 acute angle triangles? Is it possible to do that? Okay, so if that is the case, then you want all these 4 triangles to be acute, right? When you remove the vertices and do this and add the remaining angles. Now, if I call this A, B, C, D, E, F, G, H, I want you to do this as an exercise. Just add up all the angles of these 4 triangles, right? Okay, if you add up that one, that one, that one, that one, that's in one triangle. Then if you take the side triangle here, you have that one, that one, that one, that one. Then go to this triangle here, that one again, that one, that one, that one, and finally this triangle here is, yeah. So when you add up all these 4 triangles, you get the sum of the whole lot. So 4 triangle will give you 720 degrees. So yeah, anyway, you can do it like this. Just add up those 4 triangles, and you were saying that all of them are acute, right? So each triangle has got acute angles, and you can prove something. All right, I'm not going to go into that. So these, if you work it out, you'll get a contradiction. I'm running out of time, so I don't want to go into that. But you can try to prove that it's not possible to have uh, uh, these 4 triangles, 4 acute angle triangles. It's not possible, right? All right. Now let me go to the last one. The length of 2 sides of a triangle is 200 and 150. The length of the third side is also an integer. What is the minimum perimeter in centimeters of this triangle? Ignore the case where the 3 vertices of the triangle lie on a straight line. So, yeah, you got 2 sides of a triangle are 200 and 150. So if you draw the triangle, and you got 200 and 150, you want the minimum perimeter. So you got 200. Sorry. 2 sides are 200 and 150, and you want x. So you want to know what's the smallest value of x. And to do that, you need to use what you call the triangle inequalities. Because in a triangle, the sum of 2 sides of a triangle is always greater than the third side. Very important. use this many times. Sum of two sides of a triangle is greater than the third side. It's called a triangle inequality. So according to this, now you got 200 plus x is greater than 150, and you got 150 plus x is greater than 200, and you also have 200 plus 150, 200 plus 150, which is 350, is greater than x. Okay, so from this here, if 200 plus x is greater than, well, 200 plus x is always greater than 150, because 200 is greater than 150. But x, in this case here, you will see x will have to be greater than 50. You just look at this. Because at 50, it will be exactly equal to 200. Right? So x must be greater than 50. So this is the only thing which gives you the minimum x. But it said that they are all also an integer. So the smallest integer bigger than 50 is 51. Right? Because you want the minimum perimeter. So you want to work out 350 plus x is the perimeter. It's sum of all this. And the minimum perimeter will mean the smallest value, possible value for this quantity here. So you're looking for the smallest value of x. X is always bigger than 50, and it's an integer, and the smallest integer bigger than 50 is 51. So therefore, the answer is 401 centimeters. Okay, so that takes care of that. And this week's assignment I've got here. Let me just see what's in this assignment. From a square with side length 5, triangular pieces are removed from the four corners to form a regular hexagon. If the removed pieces are isosceles triangles, find the area removed. We did a problem like that. Right? Very similar. We drew at this octagon. I didn't realize that we had that this was the assignment, but I think you'd be able to do that now. If you saw how from a square, if you cut off the four corners, you can get a regular octagon. So just remember the octagon, you're going to get all the sides are equal. So therefore, you can create an equation to find the area of those isosceles triangles, the removed areas. Answer the question. Okay, so that takes care of that. I must thank you for remaining, whoever remained till now. Once again, I went beyond my time, but as you can see, these problems were quite demanding, and some of them took some time to solve. Thank you very much for coming. Let me just quickly ask if there are any issues. Okay. So are there any issues here? Is anybody has got a question to ask? I don't know whether the chat column, you didn't write anything in the chat column. I don't think you had time to do that. But if there are any questions regarding whatever we have done, you feel that, I know I went very fast, but that's how it is. This thing is recorded, so you can always go to the recording and stop it at any given point so that you can understand what I said. All right. Any questions? Okay, thank you very much. And if there are no questions, we can close up and we can stop the recording. Thank you, Khotso. Oh, there's somebody raising his hands. Is there anybody